factorizable bimodules, which are closely connected to the theory of Feynman categories, unique factorization categories. So as an illustration of that, we can consider cospans, and you notice that any graph obviously can be subdivided into its different connected components, and those generate all possible graphs. So to formalize this, let's first recall definition. So there's this notion of a free symmetric monoidal category. C box times generated by a category C. The objects are bracketed words of objects in C, and the morphisms are bracketed words of morphisms in C. So this has universal property. So if I have a functor like this would induce a strong monoidal functor like this, making the diagram compute. Okay, so given a bimodule rho such that the source and the target are both monoidal categories, we can define this horizontal extension as this following left-hand extension. So because G and C are monoidal, there's a canonical map from the words of C into the original C just by applying the tensor product. And same goes here with G. And if we conic extend along that, we get this horizontal extension. So then a bimodule would be called factorizable if there exists such a nu with this isomorphism. Okay, so consider some examples of this. So the bimodule rho cospan factorizes like this, and in fact, this new cospan is defined very simply as a singleton set for each variable, the trivial action. Another example would be finite sets. So this example is important for operads. So if we let K be finite sets, then rho fin set factorizes like this, or this basic bimodule rho fin set is simply defined like this. And you can do the same thing for a large swath of examples. So for a hereditary unique factorization category M, this determines a factorizable bimodule, which are the overlying new M's here. And importantly, it has what's called a hereditary multiplication. So we won't quite have time to get into what this means, but it's very important. Okay. So now that we have this notion of a factorizable bimodule, we can refine the notion of a Platheism product in an element representation that we talked about before. So if the structure bimodule rho is factorizable, then we can define basic element representations to be functors D from L nu to C. So this time we're only considering the basic parts. And there's a notion of a Platheism product for basic element representations when the multiplication is hereditary. And we do this by adapting the definition I showed you before. So an example of this would be a basic element representation of nu cospan to C together with the multiplication. This is precisely the data of a proper ad. So some further examples. So in our paper, we explicitly consider operads and hypermodular operads. And then we show that in much more generality, an operad-like structure can be expressed as a monoid of a basic element representation, something like this. If it's Feynman category, it can be expressed as a plus construction for hereditary UFC M. Okay. So now we can talk a little bit about algebras. So for a notion of algebra, for any notion of algebra, you have to specify sort of where the algebra lives, right? You can have an algebra in vector spaces or an algebra in topological spaces. So the role of this reference bimodule, this is the role of the reference bimodule in this context. So what this is in practice is a bimodule that would look like the following. So we would take some functor O from G to C and define alpha O to be this composition. So we just apply O to each of these variables and kind of wire it through some Hom functor. So for example, we have some O to this category of bijections into vector spaces, say defined like this. Then our reference functor would be the set of linear maps from this AK to EK. Okay. So that we can define an algebra. So like the very most basic notion of an algebra would simply be a morphism from rho to the reference one. And just a comment that in practice, these reference bimodules are equivalent to the notion of a Platheism module that looks like this, where the O is the same O as before. Okay. So you can do them on the bimodule level, but you can also do them on the element representation level. So for a fixed element representation, there are actually two different ways to define a D algebra. And we proved that those two things are equivalent. So there's sort of a bimodule version and an element representation. You'll see what I mean very shortly. So for the bimodule version, there's a way to turn any element representation back into a module. And it's done by taking this left con extension here. So this is very closely related to an idea called an index enrichment. So then a D algebra would be defined as chi D into A. Okay. And then for element representations, so classically, you would define an algebra of an operad by picking an object X in some monodal category. And then the algebra would be defined as an operad morphism from O to this endomorphism operad of X. So analogously, we have something called the reference element representation. We define it simply as this following, is this composition. So, so I probably neglected to say what this is. Sorry about that. So what this does is it takes an element in here, and then, so maybe I would have X in row AB. Then sigma would send that element to the pair it came from. So it would go to AB. Okay. So we apply that sigma functor here, and then apply alpha. And we would then define a D algebra as a morphism from D to E alpha. And remarkably, those two things are the same thing. And it turns out to be part of the defining, it comes from the defining property of left con extension. So thank you, everyone.
Are there any questions for Michael, either in the room or online? I guess one thing I was wondering is when you say operad-like structure.
Hmm.
Do you have some kind of precise notion of what that means?
Yeah, so those things would be captured by something called the Feynman category.
Right. Okay. Okay. Cool. Well, if there are no further questions, then let's thank Michael again. And we're running a little late, but I'll say we should try to reconvene in 5 minutes or 2. Yeah. We'll say 25 past.